Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Electronics Honors for the subject Analog Electronics. These are the topics we are going to discuss today. The advantages of negative feedback circuit, basic feedback topologies in which voltage series and voltage shunt feedback, current series and current shunt feedback networks. For all these feedback circuits, we are going to derive the gain input impedance and the output impedance. Generally, a feedback amplifier contains two components, namely the feedback circuit and an amplifier circuit. The picture shows the feedback circuit in which there are two potential dividers, that is resistances R1 and R2. The purpose of the feedback circuit is to feed back some portion of the output to the input signal. So, which has been shown in this circuit diagram or a block diagram. The purpose of feedback circuit is to return a fraction of the output voltage to the input of the amplifier circuit. So, how do you calculate the fraction of the output voltage through these feedback circuit? So, here beta is the gain of the feedback circuit and which can be derived as V2 by V1. V2 is the voltage across the resistance R2. So, how do you calculate the voltage across the resistance R2? By using the potential divider rule. The applied voltage into the resistance across which we are going to calculate the voltage divided by the total resistances. So, V2 is the voltage we need to calculate. So, V2 is equal to R2 into V1 divided by R1 plus R2. So, if you take V1 from the numerator on the right hand side part to the denominator to the left hand side, we will get V2 by V1 is equal to R2 by R1 plus R2. This is the feedback fraction. So, amount of this fraction is going to be sampled at the output of the amplifier and it has been fed to the input of the amplifier. So, in an amplifier circuit we can give a negative feedback as well as the positive feedback. The negative feedback returns part of the output to oppose the input, whereas in positive feedback the feedback signal aids the input signal. So, from here we will calculate what is the gain of the overall circuit, that is with the feedback, gain of the circuit or an amplifier with feedback. So, if the input if there is no feedback, consider for the case if there is no feedback, then Vf is equal to 0. So, in this circuit if you see what is Vf, that is the voltage from the feedback network given to the input of the amplifier, and Vs is the input signal, Vi is the difference between the input signal and the feedback signal. So, Vi is Vs minus Vf and V0 is the output. So, if the feedback is 0, feedback voltage is 0, so the output voltage V0 will be the gain into the input voltage, or the gain can be written as V0 by Vs. So, we know that Vi is the difference between the input signal and the feedback signal, and if the feedback signal is 0, then Vi by, instead of Vs we can write Vi. So, if the feedback signal Vf is connected in series with the input, then we know Vi is equal to Vs minus Vf. So, this voltage input signal given to the amplifier now is Vs minus Vf if the feedback is connected to the input. So, what is V0 now? V0 is gain into Vi, this voltage, this output voltage is gain into Vi. So, this triangle represents the amplifier and this square represents the feedback circuit, and the gain of the amplifier is represented as A, gain of the feedback is represented as beta. So, now the output voltage of the amplifier with the feedback network can be written as A into Vi, A into Vi, and what is Vi? It is Vs minus Vf. So, substitute Vi as Vs minus Vf, but what is Vf? Vf is beta into V naught, the gain of the feedback network into the output voltage, that is the output of the feedback circuit, it is Vf. So, Vf can be written as beta V naught, and if you substitute for Vf in this equation, it will become V naught is equal to A into Vs minus beta V naught. So, when you take this term, the total term, to the left hand side of the equation can be written as V naught into 1 plus beta A equal to A into Vs. So, from here you can obtain the closed loop gain of the circuit, that is the gain of the total circuit with the feedback network. It is written as A suffix f with the feedback. The gain with the feedback is V naught by Vs, that is the output voltage V naught and the input voltage Vs is now A by 1 plus beta A. So, what is A? It is the gain of just the amplifier, and now this gain of the amplifier is reduced by the factor of 1 plus beta A if the feedback is given to the circuit. So, the gain is reduced by the factor of 1 plus beta A. And what is AF here? AF is the closed loop gain of the amplifier and A is the open loop gain of the amplifier. So, we now seen that if a negative feedback is given to the amplifier circuit, it reduces the output signal, and ultimately the gain of the circuit is also reduced. We have seen it as A by 1 plus beta A. So, this 1 plus beta A is the feedback reduced rate. By this rate, the gain of the amplifier without feedback is reduced. So, we know that what is A and what is beta. A is the gain of the amplifier and beta is the gain of the feedback circuit. So, for the negative feedback, the product of A beta must be greater than 0, and for the positive feedback, the product must be less than 0. So, what are all the advantages of the negative feedback? Even though the gain is reduced by the factor of 1 plus A beta, this has some advantages, and they are gain stabilization, reduction of nonlinear distortion and noise, control of input and output impedances, and extension of bandwidth. So, gain will be stabilized if you give a negative feedback, and linearity will be improved. The input output impedances, we are going to see how they are going to be controlled, and the bandwidth is increased when you give the negative feedback. So, this, when you look at this graph, this shows that improvement in the linearity of the amplifier circuit. So, here it is the input voltage is taken along the x axis and output voltage is along the y axis, and this curve A is the curve for the amplifier without feedback, and this curve B represents the amplifier with the feedback. When you compare these two curves, the linearity is more for the curve B. So, if you give feedback, negative feedback to an amplifier, the linearity is improved when you increase the input voltage, the output voltage is linearly increased from this point to this point, and after that it is saturated. Similarly, for the negative side also. And when you go to the bandwidth extension, and we know that how can we calculate the bandwidth. So, bandwidth is the parameter which can be calculated by taking the difference between the higher cutoff frequency and the lower cutoff frequency, and it has been plotted in the Bode plot. Bode plot is one of the Bode plot. It is frequency versus the gain of the amplifier. So, frequency is in the x axis and gain is along the y axis. This curve is for the amplifier without feedback. The greater one is for the amplifier without feedback. So, from here we know that the gain is maximum for a particular frequency, and after which if the frequency is increased, the gain is reduced. This is what we have seen in the previous classes. So, now what happens if the negative feedback is given? So, the gain is reduced. Just now we have seen A by 1 plus A beta, where 1 plus A beta is the factor by which the gain without feedback is reduced if we give a feedback. So, the gain is reduced from this point to this point, and if you compare the bandwidth between these two curves, so the bandwidth of the amplifier with feedback is extended. So, here this is the bandwidth, this B is F1 minus F2, and the B suffix F, that is the amplifier with the feedback, the bandwidth of the amplifier with the feedback is extended, where you can see FLF minus FHF or F1F minus F2F. So, the bandwidth is extended if you give the negative feedback to an amplifier. How the gain is stable? So, this can be proved in a problem. We will see it in the we will see it later, the problem. Now, you can look at the equation here. If you differentiate or if you see the relative change in the gain with the feedback, it has been derived as 1 by modulus of 1 by beta A into the relative change in the gain without the feedback. For this case, beta A must be greater than 1. So, this shows that the magnitude of the relative change in the gain with feedback is reduced by the factor A beta compared to that without feedback, dA by A. So, that is a exercise in which the gain of the amplifier without feedback is given in two values. So, one is a higher value, the other one is the lower value. So, if the feedback is given, what happens to the gain? That is the question for that problem. So, by doing the problem, we can come to a conclusion that the gain is stabilized in that case. We will see the problem later. And now we are going to see the basic feedback topologies. Depending on the input signal, voltage or current, the current or voltage may be the input signal to be amplified, and form of the output, this again can be a voltage or current. The amplifiers can be classified into 4 types, and depending on the amplifier category, one of the feedback structures can be used. So, what are the 4 types of feedback networks? They are voltage series feedback, and it can be otherwise known as voltage amplifier, voltage shunt feedback, otherwise known as trans resistance amplifier. Why it is trans resistance amplifier? If you look at the voltage, if you look at the gain of the network, it is V naught by Is. So, V by I, which means that it is a resistance, and this is the output voltage and this is the input current, and so it is trans resistance amplifier. And current series feedback, it is I naught by Vs, again it is trans, this is the output current and this is the input voltage, so it is trans. It is conductance because it is I by V. By Ohm's law, it is V is equal to IR. If you look at if you see the formula for the resistance R, it is V by I. So, it is resistance. If it is reverse, then it is conductance. So, it is a trans conductance amplifier, and current shunt feedback, it is a current amplifier, output current by input current. So, these are the different types of feedback networks we are going to see now. And if the we have seen that voltage series, voltage shunt, and current series, current shunt. What do you mean by voltage current in the network's connection? So, how will you connect the output to the input if it is voltage is the case, and if the current is the case, how will you connect the output to the input? Voltage refers to connecting the output voltage as input to the feedback network. So, we are connecting the output voltage as the input to the feedback network, and current refers connecting the output current as input to the feedback network. So, if you take voltage at the output, you have to take it parallel connection, and if you take current from the output, you have to take a series connection. So, we will see it later how you are going to connect the output voltage or output current as the input of the feedback network. And when you see a series or a shunt, so series refers to connecting the feedback signal in series with the input voltage. So, this is what you have to look around, input voltage. Series refers to the connecting the feedback signal in series with the input voltage and shunt parallel with an input current source. Okay. Series is you have to give a input voltage, and shunt means you have to connect it with an input current. So, series feedback connections tend to increase the input resistance, while shunt feedback connections tend to decrease the input resistance, because series, if the resistances are in series, we know that you have to add the resistances. So, the final resistance will be increased. For shunt connection, it is a parallel connection. So, if you calculate the parallel combination of the resistors, then ultimately the resistance, effective resistance will be reduced. That is what, if you have a series connection, the resistance will be reduced, impedance will be reduced, and for shunt it will, series it is increased, and for shunt it is reduced. The voltage feedback tends to decrease the output impedance. Why? Why the voltage feedback tends to decrease the output impedance? Because just now we have seen, if there is a voltage term present in the network, then voltage, you have to connect the output voltage as input to the feedback network. So, how will you connect the output voltage as input? You have to take parallel connection. So, from the output you have to take the voltage parallelly, and you have to give it to the input of the feedback network. So, voltage feedback tends to decrease. So, if you have a parallel connection, it means that there exists the parallel combination of two resistances. So, it will decrease the output impedance, while current feedback tends to increase the output impedance. Typically, higher input and lower output impedances are desired for most cascade amplifiers. Both of these are provided by using voltage series feedback network. So, you can see from the heading itself, voltage means you are connecting the output voltage to the input of the amplifier, and if it is a voltage, you are taking it parallelly. So, the output impedance is reduced, and if you connect it series to the input voltage, then the input impedance is increased. That is why the voltage series feedback connection gives you the higher input impedance and lower output impedances. So, these are the different types of feedback networks. It is a voltage series feedback. So, when you see the output side, how the output voltage is given as the input. So, for voltage you have to take parallel connection. So, by this way you have to take the output sample of the output and given to the input of the feedback network, and here it is series. So, the output of the feedback network is connected in series with the input voltage. So, this is very important. So, if it is series, the output of the feedback network is connected in series with the input voltage. If it is shunt, there must be a current source. There must be a current source, and here the output signal will be connected parallel to the input current source in that case. So, now we are looking for voltage series feedback. So, for which the gain of the circuit is V0 by Vs. This is V0, the output voltage, and this is Vs, the input voltage. So, we know that the voltage series feedback is a voltage amplifier, and the amplification factor is the output voltage by the input voltage. And next is voltage shunt feedback. Voltage shunt feedback. Voltage means you are giving the output part of the output voltage to the input of the feedback network. Again, if it is a voltage, you have to take a parallel connection, that is shunt connection, and you are giving it to the input side by shunting the output of the feedback network to the current source, because it has the shunt feedback network. If it is shunt, it must be a current source. So, the output of the network is also connected in parallel to the input current source. And what is the gain of the total network? It is output is V0, input is Is. So, V0 by Is, V by I, it is a trans resistance amplifier. And next is current series feedback. So, current means you have to take the output current. Output current can be taken in series, and this is given as the input of the feedback network, and if it is a series feedback, the output of the feedback network is in series with the input voltage. So, series means input voltage, the connection is also series between the output of the feedback and the input voltage source. And what is the gain of the circuit? It is I naught by Vs. Output is the current, we have taken it current. So, I naught by Vs is the input voltage. So, it is a trans conductance amplifier, and here it is a current shunt feedback. Current, if you are taking current from the output, it has to be in series, it is given to the input of the feedback, and output of the feedback is connected in shunt with the current source. And what is the gain of the network? It is I naught by Is, because in both the sides current is the parameter we are going to measure. So, it is a current amplifier. So, we have seen all the different types of feedback networks with its overall gain, and also we know that what is the gain of the feedback network. Gain is it is defined as the ratio of the input to the output. So, in the case of voltage series, it is the input voltage is output voltage is V naught, that is the input for the feedback network, and so output voltage is Vf. So, Vf by V naught here. Similarly, for all the feedback circuits, you have to see what is the gain of the feedback circuit. Next is voltage series feedback. So, for which we are going to derive the gain with feedback. We know that for all the networks the gain is reduced. We have seen in general A by 1 plus A beta. The same result has been obtained for the gain with the feedback for this circuit. It is the detailed circuit for voltage series feedback. Okay, so it is the gain of the voltage series feedback network with the feedback. Okay, with feedback. A is V naught by Vs, and V naught can be represented as V naught itself by Vi. Vs is Vi now without feedback. In this case, there is no feedback. So, which means that A is the gain of the amplifier without feedback. If the feedback is given, this case is different. So, we know that Vi is the difference between the input signal and the feedback signal, and if it is substituted and finally we obtained, as in the previous case, we obtained the gain with the feedback is A by 1 plus beta A. So, the gain with feedback is the amplifier gain reduced by the factor 1 plus beta A. And for voltage series feedback, the input resistance of the amplifier and feedback network are in series, hence the effective input resistance will increase. We know that it is series connection. So, series feedback in the sense the output of the feedback network has to be connected in series with the input voltage. So, if it is series at the input side, the input impedance will increase, and you are taking output voltage now. So, when you calculate the output impedance, if you take voltage, it has to be parallel. So, if you have a parallel combination of the resistances, then the output impedance will be reduced. So, here there is a parallel connection. So, if it has the resistance here and the output resistance of the amplifier, these two resistances are reduced now because you have a parallel connection, and here there is a series connection, and so the resistance of the feedback as well as the resistance of the input will increase now. So, this is what the requirement for any amplifier, the input impedance must be high and the output impedance must be low. So, now we are going to derive the input impedance with feedback. If you see the circuit, this is the input source Vs, and this is the actual input Vi is given to the amplifier without feedback, and what is Vi is the difference between this input signal and the feedback signal, and the V naught is taken across this resistance RL. And what is the factor, what is the gain of the feedback network? It is beta is equal to Vf by V naught. What is Vf? It is the output of the feedback network, and V naught is the input of the feedback network. So, always gain relates the output by input. It is the ratio of output by input. So, Vf by V naught, And what is Vf now? Vf is equal to beta V naught. So, this has to be used in the calculation now. The input impedance can be determined as I, that is the input current, which can be written as the input voltage divided by the input impedance. We know that if it is with feedback, input voltage is the difference between the source voltage and the feedback voltage, and this feedback voltage is replaced by beta V naught, we have seen just now. And beta V naught, here V naught is the output of the circuit, and this can be written as AVI, that is this voltage AVI. This is the output voltage. The parallel resistors all will have the same voltages. So, V naught is AVI. Now, this Z1 is brought to the left hand side. So, I1 Z1 is equal to Vs minus beta AV1, and Vs is equal to, from this Vs is simplified as I1 Z1 plus beta A I1 Z1, and from here if I1 is taken out, you can have Z with, that is input impedance with the feedback. So, Vs by I1 is equal to Z1 plus beta A Z1, and if you take Z1 out, it is Z1 of 1 plus beta A. So, when you look at the input impedance, as we told, the input impedance is increased because the connection is in series. It is a series feedback. So, input impedance is increased by the factor of 1 plus beta A. So, always the impedance or the gain, whether it is increased or it is decreased, the factor is the same, 1 plus beta A. If you look at the gain, it is 1 plus beta A times the gain of the amplifier without feedback is reduced. We have calculated the input impedance. Here 1 plus beta times it is increased. The input impedance with series feedback is seen to be the value of the input impedance without feedback multiplied by the factor 1 plus beta A. We know that what is beta and what is A. Now, the output impedance. So, what may be, before calculating the output impedance, what may be the output impedance? We know that it is the output voltage taken as the input of the feedback network. So, how will you take the output voltage? It is by the parallel combination from the output side. So, if you have a parallel connection, then the resistances will be reduced. So, the output impedance will be reduced by the factor 1 plus beta A. So, when you look at the derivation, so this is the common method to find out the output impedance. You have to short the input source voltage Vs. So, Vs is equal to 0, and you have to apply a voltage at the output side, and that is the voltage V, and by this voltage you are getting a current I. So, from this you have to start the calculation. The voltage V is given as V equal to, that is the voltage applied at the output side, V equal to I Z0 plus AV1. So, this is the voltage source which is in the transistor side, and this is the current due to this voltage V. So, equivalent V is taken as I Z0 plus AV1, and this V1 is minus Vf, because when you look at the circuit, actually if Vs is equal to 0, this is the case we have started before the calculation. Vs is shorted. So, we know that it is the algebraic sum of the source voltage and the feedback voltage. So, Vi will be minus Vf if Vs is equal to 0. So, Vs minus Vf is actual equation. So, if you put Vs is equal to 0, then Vi is minus Vf. So, you substitute this value here, then it will become I Z0 minus A Vf equal to I Z0 minus A beta V. And finally, you can obtain this equation Z0 by 1 plus beta A. So, by this factor, the output impedance Z0 is reduced for the voltage series feedback. So, as we have seen, the voltage series feedback contains the higher input impedance and lower output impedance, and so this is a normal amplifier's expectation to be a good amplifier. So, in this session we have seen the advantages of the negative feedback amplifier and basic feedback topologies, in which varies in which voltage series, voltage shunt, current series, current shunt feedback we have seen, and we have seen the derivation of gain input impedance and the output impedance of one particular feedback network. The remaining we will see it in the next session. Can you answer for these questions? What is a feedback amplifier? List the types of feedback network. Which feedback amplifier will work as a current controlled voltage source? You have to guess this. And how the input impedances are affected by the feedback factor. List the advantages of the negative feedback. These are the references. Thank you.